I want to set the context a little bit for the business of the national labs and the stockpile challenges. I took over the weapons program at Sandia in 1991. At the time, the three labs had three principles that we tried to advance as the Clinton administration and Dr. Vic Reese came into control of the Department of Energy and the weapons program. The three principles were to advance the state of high-performance computing, which had been in somewhat of a hiatus for almost a decade. The second one was to maintain the vitality of three labs, even at a time when there was questions about whether or not we really needed three labs. It was our view that we really needed that in order to have the competitive environment to advance the science that would be necessary. And the third leg of this was experimental validation. And from our three speakers, you're going to hear some about each. I want to set the historical context in the following way. We had a meeting at Stratcom now some more than 20 years ago when the weapon directors from the labs met with the Secretary of Energy, Deputy Secretary of Defense, the head of Stratcom, and about 50 people that were senior military and civilians in the nuclear deterrent area. And the reason for the meeting was to decide whether or not we could continue to maintain a safe, secure, and reliable stockpile in the absence of nuclear testing. As you probably know from the Carter administration, where it was the #1 priority was a test ban, through the Clinton administration where a test ban was a very high priority, we were directed to have this meeting to decide whether or not we could maintain the stockpile. In a very private session after the meeting, presentations from the labs, the lab directors along with the Secretary of Energy and the Deputy Secretary of Defense and the head of Stratcom made a decision on a close vote that we could. And the Secretary of Energy conveyed that decision to the President shortly thereafter. Secretary of Defense, Perry, concurred with the decision because he felt that the expertise of the laboratories in the Department of Energy was paramount in making that decision. The next step in the history was a meeting with the NSC, Assistant Secretary of Energy Vic Reese, the lab weapon managers, and the senior financial people from the Department of Defense and the Department of Energy. And the decision that was made at that meeting was to increase the funding of the weapons program to ensure that the means to advance the computing and the science and the experimentation necessary to provide confidence in the stockpile in the absence of testing would be funded. That is the beginning of what we call the Stewardship program. It's now more than 20 years old. At the time, there was considerable trepidation from all of us, including those that supported a rapid movement to the test ban, about whether or not we could, in this unprecedented fashion, such that we could, in fact, have confidence in a stockpile where the electronics essentially were designed in the era before the presence of the first Apple and PC computers, and where the pits, or the central part of the weapons, were designed actually back in the 70s. And so that was the beginning of a program where, as I said, we had considerable trepidation, and it sort of ran along the following lines, and you'll hear comments from our speakers relevant to this. It's not a matter of, it's like two clocks running down. One of them is very slow, and that's the stockpile. It is a very robust system. The other clock that runs down is our capabilities, our knowledge, and the expertise of our people, which on average takes 15 or 20 years before you run out of the people that were responsible for the design. So as we face this trepidation, we now look 20 years later into the question of the challenges of the stockpile and the role of the national labs. So with that, I'd like to introduce our first speaker, Mr. Bob Webster from Los Alamos National Lab, to be followed by Lawrence Livermore Lab, and then by Sandia. Bob?
I hope I have slides. That's Steve's. But I'll speak for Steve. It's okay. Well, I'll just start and wait for the slides to catch up. And I'll skip straight to the second slide. Los Alamos is busy. I'm going to talk mostly about how we do our work. So from Admiral Haney, you heard what needs to be done in terms of deterrence, modernization. Do I control this, or can I go to the next slide? Yeah. And I'm going to talk about how we at the scientific laboratories do the work of maintaining the stockpile. So Los Alamos, we're proud of the fact that we're the design laboratory for the majority of the on-alert deterrent. By that, what I mean, because these pictures are not what we're responsible for. We're responsible for most of the NEPs that are out there by pure count. So we're the design laboratory for the B-61 bomb, the W-76 warhead, the W-78 warhead, the W-88 warhead. And when we talk about being the design laboratory, what we really mean is that Los Alamos is responsible that the nuclear explosive packages that are delivered by these things, and we can't show the nuclear explosive packages here, which is why we show the delivery vehicles instead, provided they get where they're supposed to get, and Sandia's parts all work, we're responsible to tell you that the nuclear explosive package will provide the yield that it's asked to, and that it won't do it anytime that you don't ask it to provide yield. So they've got to be safe, and they've got to be reliable. So the next slide. I have the control here. And I'm there. Okay. So we do that, we use science and engineering to underpin everything we do in making those decisions. But this is actually not new, and this is something that seems frequently to be missed as we talk about science taking over after underground testing. We actually underpinned our understanding of the nuclear weapons even when we were testing through science and engineering, because it wasn't possible to test the weapons in every delivery scenario, every hardship, every feature of aging that showed up. We always had to extrapolate from where the nuclear tests were through our science and engineering basis. Towards the end of testing, what the tests really gave us that we can't reproduce today was an integral test of the system and the ability to do science and engineering at scales of large sizes, very dense materials, very hot materials that are typical of a nuclear weapon. You cannot get matter into that state outside of a nuclear weapon. So what we do instead, and what the Stockpile Stewardship Program put in place, was an alternative approach to understanding how material behaves in that situation. And you see here pictures of different types of experiments that we do. So we do experiments, for example, the high energy density physics experiments at NIF. They're hot, they're dense, they're small. We can't get all three at the same time. We do in the lower right large explosive integrated tests. They're big, they've got the right scale. They can get pretty dense, but they don't get hot. And we use our science and we use the computers that we had let lapse as we were running into the stewardship program, and we've invigorated a lot to extrapolate from all of those different regimes and form scientific principles where we can measure, and then extrapolate them down to the nuclear weapons with our computer tools, benchmarking that extrapolation is correct against the underground test history that we have. Let's see. Which way? Okay. To do that science requires infrastructure. And here you see some examples of infrastructure from around Los Alamos. So we've got a building dedicated to high-performance computing, where the computing floor is slightly larger, it's maybe twice the size of this room, full of supercomputers that are used to evaluate the performance of the nuclear weapons. We have high explosive laboratories where we keep testing explosives, making sure that they're not aging in such a way that they're not unsafe, and in such a way that they will perform. We do neutron science because you can't really understand a nuclear weapon without understanding how neutrons and nuclear cross-sections work. Plutonium processing facility, we are the plutonium manufacturing plant for the country and one of the plutonium R&D facilities for the country. The CMR building, an old building that frankly needs to be replaced. It dates from sort of just post-Cold War, Cold War-ish era. One of the facilities that the dual-axis radiographic hydrodynamic test facility, this is where we test, to the extent that we can, short of going in a nuclear weapon, the modern implosion techniques, and see that changing out the high explosive, putting in replacement high explosive, because the materials all age out after a time. We have to refresh these systems. Forgot to mention on that first slide, we are in the middle of an LEP for the 76, and that requires almost daily feedback from the laboratory on the status. Are we being safe? Are we doing things right, and will it work? We're in the middle of a B6112 LEP study to try to develop the life extension program for that. In particular, our laboratory is involved in the nuclear explosive package. And we're in the middle of a fairly major alt for the W88. So the laboratory is very busy using these facilities to underwrite that what we're doing on those efforts is right. We also have major investments in waste handling that are being required, dominated right now by cleaning up the legacy of what was done decades ago at Los Alamos. There's a lot of work to clean that up at the moment. Okay, so at the inception of the stewardship program, and it really came down to people, as was pointed out, we were really worried that we would lose the skills and the people and they would get reckless. We were worried about having hubris show up. And we're not doing a nuclear test anymore, but we're trying to replace it there with the DART facility, the supercomputers, building up our ability to do that. We were worried in the process of doing that hubris could develop. Now, 20 years later, things are changing somewhat. The stewardship problem has moved just from being able to understand button-to-boom performance of the weapon to the whole life cycle, being a little bit more aware of the impact we have today as we're doing the work. So all the way from production through to the final disposition, through to turning pits into mocks and getting them out of the thing. The science of stewardship underwrites all of that. So I've got pictures here on the right. The upper right is an example of plutonium casting, trying to do plutonium work in such a way that we generate less waste in the process of doing it, down to the waste drums that we have to do. And all of that is so that in that bottom row, our director, Charlie McMillan, can inform the Secretary of Energy and then the President on the status of the stockpile. Do we believe, based on the observations from surveillance that we've got, that the thing is still safe, secure, and it'll work if you send it? Okay. That really, the big challenge then that comes is recruiting a workforce that can do this. We have to have the facilities, we have to have the infrastructure, but it's no good without a workforce that can use it. And here you get an illustration of the challenge that faces us. In that panel on the upper right, at our 70th anniversary, we had a panel discussion between senior designers about their thoughts on the evolution of hubris, where we were, how the stockpile stewardship program was working. The three members sitting to the right are people who actually had test experience underground in Nevada. The three people sitting between them and me are middle-aged, and you notice how gray even they are. There are middle-aged designers. The challenge is moving the information, the thought, from them down to this group in the lower right. To do that, because the LEPs don't really drive a lot of design. A lot of it is caretaking and fairly It drives assessment of the stockpile very well, but not the whole process of thought of design. We focus these teams as they're coming through on prototyping and looking at the foreign nuclear weapons. We give them a chance to see what other people are doing, because frankly their programs are a little bit more aggressive than ours in looking at what is the art of the possible. That's just the way that we're doing it right now. Of those folks in that lower right, that's a picture from 2 years ago, 2 of them have moved on to become our current stockpile stewards. So they are the POCs that have moved back over and are responsible for assessing the stockpile that we've got. I think I'll skip to the next slide. I was going to point out it takes a big campus to do all of that. But just to wrap up then, stewardship is not static. We had a vision of stewardship 20 years ago. We've largely come through on that vision of stewardship, but things have changed. The importance of waste streams is bigger today than it was when we were looking at it. The age of the weapons and the distance of the designers that we've got available from us compared to the test history is larger. And so we're evolving. In the right, you can see we've evolved from that historic complex, which was massive. You can move massive amounts of material through that complex, down to, in the middle today, PF4 and Y12 in particular for the S&M, pretty limited in the ability of moving material through what we've got. And moving to the future with a plutonium strategy that'll involve modules and a new facility at Y12, where we can both move adequate amounts of material to be responsive and do it without generating a lot of waste and a legacy. In parallel with that, the experiments have changed. We went from the underground tests to the middle one where we've got NIF and DART and the facilities that were built as part of the stewardship program. And we're looking out forward to new material science capabilities where we've got a better ability to predict how the materials will age and respond. This middle step system that we've got is very good at answering the question, given what you've seen in the stockpile today, will it work? It's not perfect at saying, and will it work 20 or 30 years from now? The science that underwrites that's a little weaker. And new facilities downhole. And then up above, computing underwrites it all. The only place we can bring all the scientific theories together and understand the performance of the nuclear weapons is through the high performance computing. And we will continue to have to push that.
Our next speaker is Dr. Charles Verdon from Lawrence Livermore Lab.
If I could have my slides. So let me start first by saying these bandages on my face aren't a result of the organizers convincing me to be here. It's a pleasure to be here this morning. And you'll see when my slides come up that there'll be similar themes, obviously, between what Bob presented and what I talked about, well, I'll talk about. So if I could have the next slide, please. You want me to do it, or you can do it there? Okay. So, yeah, you can do next slide. Okay, never mind. So Lawrence Livermore is a national security laboratory. We work on broad national security. We work on nuclear security, international and domestic security, and energy and environmental security, and it's underpinned by applied science. We really do focus on applied science, even though there is basic science that we do within the lab, but it's really focused on the missions that we're trying to support. Engineering, we do like to build things, we do like to construct things, and then computing, similar to what Bob said, computing does underpin a lot of what we do, and it may come as a surprise, but actually the first thing ever procured by Edward Teller, one of the founders of our laboratory, was actually a computer. Everyone thinks of him as a theorist, but it was computing. So next slide, please. So at Livermore, our nuclear security mission is anchored by the Stockpile Stewardship Program. I tend to look at it as three major pieces. Our first piece is maintaining the current stockpile. I'll highlight our responsibilities there. The other is extending the stockpile, extending the life of the stockpile, conducting the life extension programs and the modifications. And then equally important in our mind is the long-term stockpile sustainment, making sure that we're developing the capabilities that are not only needed for today, but are needed for the future. And what will underpin all of this, obviously, is our workforce, our science and technology, and our facilities. So next slide, please. So our responsibility for the present stockpile, we have three nuclear warheads in the stockpile that we're responsible for, the W-80, the B-83, and the W-87. Air-launched cruise missile, gravity bomb, and a reentry system. The number one, our view of the number one driver or number one deliverable for the laboratory is to conduct the annual assessment. As the name indicates, annually we assess the status of the stockpile. That's our number one deliverable. We support limited life component exchanges and develop safety and security features that are to address evolving requirements. So that, as I say, our number one job is care of the present stockpile. Next, please. In terms of life extending the stockpile right now, one back up, please. We have lead nuclear design laboratory responsibility for the W80-4 LEP and the W78-88-1 LEP. Right now, the W80-4 shown there is in a phase 6.2 feasibility study, which was initiated in 2015. And the phase 2, 6.2 for the W78-88 was paused and is planned to restart now in 2020. But that's, we're actively working right now on the W80-4. Next, please. Similar to what Bob said, our science, technology, and engineering, it really informs all of our stockpile decisions. It sounds like it's easy to say, but it's not. It really does. It's our people that inform all the stockpile decisions, but their judgment is informed by our knowledge of the science, technology, and engineering. We have our past underground tests. We have our experimental facilities where we pull the physics apart and we reintegrate it back together again through the use of our high-performance computing. So if you go to the next slide, please. What you can see there is the fact that we use a wide spectrum of experimental facilities to do our job. And this becomes apparent, some people have often asked, why do we have to have so many facilities? And it's kind of like what Bob said. It's one of the few things in nature where you have to worry about something that has to perform at sub-zero temperatures to ultimately temperatures in the interior of a sun. So examining, understanding how material performs across that wide spectrum results in us having to have this wide capability of understanding where we can understand how high explosives are both developed and how they work. The hydrodynamic experiments, as Bob mentioned, what we use are a contained firing facility at Livermore and the DART facility at Los Alamos. Actinide science, we still have to do a lot of research yet on understanding the fundamental principles for actinides. The high energy density physics, again, where we get to the conditions in the center of a Jovian planet or a star, the NIF and the Z facility at Sandia. Also, advances in manufacturing, as I'll come back to. This is something that we have to think about as we go forward, that trying to maintain Cold War manufacturing capabilities into the future are proving to also be a daunting task. So how we actually can take advantage of a resurgence or a renaissance in manufacturing to inform future stockpile endeavors is something that we work on, from designing materials and structures to just new manufacturing techniques to reduce the amount of waste and more efficient processing, all again supported by computing, and obviously all there to inform the key judgment of our people. Next, please. In terms of our facilities, Livermore does have a number of key stewardship facilities on our main site. The high explosive application facility, this is a facility where we can right on site develop high explosives, study high explosives, how they perform, and also conduct 10-kilogram explosions on site that you wouldn't even know we were doing because they're contained within large vessels. The National Ignition Facility is located at Livermore, again, where we assess the regimes that you find at the center of Jovian planets, the stars, to understand how materials perform under those exotic conditions, where before we could only access through underground testing. Our superblock facility, where we study actinides. High-performance computing facility, where, again, we integrate all the physics back together again and to make assessments of how the weapons will perform, both as they're sitting in deployment or potentially ever, God forbid, have to be used. And our precision engineering, where we actually do our engineering work to make sure that the warheads will live and behave correctly throughout their life cycle. Next, please. Livermore also has a site about 15 miles to the east called Site 300, where we can do other important experiments in support of the stewardship program. In particular, we do our large-scale high-explosive testing at Site 300. This is also where a contained firing facility exists, and also where we can do engineering testing using mock S&M, but live explosives to make sure that we can expose the weapon to as much of the stockpile to target sequence as we possibly can using these types of test facilities to gain confidence that the weapon will work as designed. Next, please. We also, this is part of the theme of making sure and how we utilize and leverage our science, but also how we begin to train and expose our people to a broader spectrum of problems, so that we're beginning to, offer them the opportunity to be tested across a wider regime of relevant deterrent missions. Our stewardship program takes advantage of both spinning out technologies to a broader national security mission shown on your right. We do this again to leverage the country's investment that it makes in the stewardship program to support these broader national security efforts, but also because we get benefit back from that, where we bring back technology, we bring back, again, our people get a wider spectrum of problems of which they can address, and they learn that Mother Nature can be tricky, and bring that information back with them to the weapons program. So we take this approach, to the benefit of the broader national security, but certainly the benefit of the stewardship program. Next, please. And then finally, I'll say that, I believe that the stewardship program has had many successes, but more remains to be done to ensure safe, secure nuclear stockpile for the long term. As I mentioned, there are some science objectives that still identified at the inception of stewardship that remain to be solved. We have, as the Admiral Haney mentioned this morning, we have ongoing and planned life extension programs that we are committed to fulfilling. We see on the horizon that new innovations are needed. I mentioned advanced manufacturing to increase the responsiveness of the complex. 21st century surveillance, less reliance on destructive testing. New safety and security themes, that's a lot of what underpins what we do with the life extension programs, not only to ensuring their effectiveness and they continue to meet the deterrent requirements, but where possible, offer new safety and security options. The other, I would say that the other really important thing that I think is being touched upon is to continue to provide opportunities for our workforce to acquire the skills, knowledge, and abilities needed to participate, anticipate and respond to future challenges. This is something that we devote a lot of effort to. As we mentioned, LEPs, that's certainly a part of it. We also use work on conventional munitions as a way to do this, the high explosive tests, the tests that we do in support of stewardship. All of those types of activities fold together. That is really important as ways that we provide our workforce this opportunity. We're constantly vigilant for ways of doing this to make sure that we're providing those opportunities to test our workforce. As I say, Mother Nature still has secrets it's withholding from us, and we have to recognize that she's always tricky. And we have to make sure that our workforce understands that they both have to know when they understand something deeply, but equally important, they have to understand what to do when they don't understand something, but also still to be able to move forward even in those cases. Because oftentimes you can't just say, well, let's wait 10 years till we get the answer. You have to make decisions and move forward. So with that, I'll end my introduction to Livermore. And
thank you, Charles. And our next speaker is Dr. Steve Rottler from Sandia.
Good morning, everyone. It's my pleasure to be here, and I want to thank the organizers on behalf of all of us, for inviting us to participate in this morning's symposium. I distinctly remember in late 1994, I switched jobs at Sandia and came to work for Roger, who at the time was my skip level manager. Shortly after I came to work for him, we had one of our annual budget reviews with the NNSA. And Roger asked me down through the chain to give a presentation. It was sort of my first opportunity to take advantage of what I'd learned in the few months I'd been in the job and help the program. And I distinctly remember being incredibly nervous at presenting in front of this large room of people on a topic that I was relatively new to, and especially in front of my skip level manager, who was a senior vice president at the time. And I find myself even now having a little bit of sweaty palms. I'm having memories of that time in 1995, and here I am presenting in front of him again. I want to give just a brief introduction to Sandia National Laboratories, and then we'll have time for some Q&A at the end. I'll start out with just a quick video that'll tell you a little bit about the history of the lab, and then I'll talk about our mission. Well, as you can see from the video, our history began with our core mission. We were created in the late 1940s as a nuclear weapon engineering lab, but like our sister laboratories over the last nearly 70 years now, our mission has broadened considerably to the point to today where we really are a national security lab in all dimensions. I'm going to divide my brief remarks here this morning into three basic parts of the laboratory. I want to make a few comments about our core mission, nuclear weapons, and then I'll say just a few words about the research base that underpins that and talk a little bit about the relationship between what we do in our core mission for nuclear weapons and work that we do for other parts of the government. The view graph that you see before you here is our way of depicting our national security mission. At the bottom of the rectangle that you see, or the square you see on the left side of this view graph, you see our core mission, nuclear weapons. It's the reason the laboratory was founded in the late 1940s. It's hard to imagine today, if the country were creating an institution like Sandia, it's hard to imagine the country creating a place like Sandia were it not for this uniquely governmental responsibility of providing national security, in part through nuclear deterrence. Over the last nearly 70 years now, the government has made a significant investment in our laboratory and in our sister laboratories and the production complex that we work with, that has led to the development of a wide range of scientific and engineering capabilities, which we refer to as our foundation. It's a coupling of our research base, the people who work at the laboratories, and the facilities and infrastructure that we have. And of course, that what we refer to as our Scientific and Engineering Foundation, that exists to make it possible for us to carry out our core mission. But we have learned over the decades how to take those capabilities and use them in ways that allow us to do equally unique and impactful things in the domain of national security for other government agencies. And in the rows above our core mission, you see 6 other mission areas in which Sandia is very visible and making unique and impactful contributions. And they range all the way from preventing the proliferation of nuclear weapons and materials, addressing threats in the cyberspace, supporting the warfighter, reducing global and chemical and biological dangers, helping the country create a secure energy future and one that is sustainable, and last but certainly not least, helping our country assure that we have sensing and detection capabilities that can be used in space in support of the country's national security. Now, with regard to our core mission, nuclear weapons, our basic responsibilities are shown on this view graph. In the upper right-hand corner, you see the basic elements of a nuclear weapon for which Sandia is responsible. We work in partnership not only with our sister laboratories, but with the production plants, with the Department of Defense, the NNSA, the services, the United Kingdom, a very large community to make it possible for us to have a secure and sustainable deterrent. Sandia's basic responsibility historically and even today has been in partnership with our sister laboratories to provide the things that have to go around a nuclear explosive package to make it a militarily useful weapon. So as is shown in the upper right-hand corner, you see we have responsibility for things like the gas transfer systems, neutron generators, components that are very essential and play a key role in the operation of the weapon. We're responsible for the safety and security subsystems that assure the weapon can be, that the weapon will operate as it's intended to in the environments for which it's intended and at the time for which it's intended. But as Bob said a moment ago, under all other circumstances, it is virtually impossible for that weapon to be operated. In the upper left-hand corner, in the upper left-hand corner, Sandia also plays a key role in partnership with our sister labs in delivering an engineered and integrated system. And of course, our role in that, as the role of our sister labs, varies depending upon which part of the triad that you're talking about. In the lower right-hand corner, Sandia does have some responsibilities for production. We have a very limited production mission. 2 key classes of things that we produce. We produce neutron generators. This is a mission that was assigned to us during the last major consolidation of the nuclear weapon complex in the mid-1990s and goes with the design mission that we have for neutron generators. Sandia also has an important production responsibility for trusted radiation-hardened microelectronics. In fact, it is, if there is such a thing as from a capability perspective, as a technical heartbeat of Sandia, I would say it is our trusted microelectronics capability that has become that over the decades. It is pervasive across everything that we do. And then in the lower left-hand corner, as my colleagues have commented, another essential part of our work is developing the capability base that makes it possible for us to carry out this mission. At our lab, just as at our sister labs, things are very, very busy right now. We have a workload that is unlike anything in the nuclear weapon program that we've experienced in close to 3 decades. We have 5 major programs underway. They're shown here. Didn't advance, did it? Yeah. We have 5 major programs that are underway right now and are shown on this view graph. The 2 that are the most mature are the B-61 Life Extension Program and the W-88 Alt 370. The W-80-4 Life Extension Program is just getting underway. It's in the early stages of planning and developing budgets, eventually leading likely to full-scale engineering development as is underway today with the 61 and the W-88. We also have a major program for the Air Force in supporting them in modernizing the fuse for the Mark 21 RV. And then another program that is just getting started is the development of the Mobile Guardian Transporter, which will replace the transporter that is used today by the NNSA to move weapons around the country. Sandia has responsibility for the design of the trailer and everything inside the trailer. The tractor is done by a private contractor under contract to the NNSA. And then in the upper left-hand corner, I saved this for last because we consider it job number one, and that is assuring the day-to-day safety, security, effectiveness, and readiness of the existing stockpile. The picture you see there is a picture of our lab director, Jill Ruby, signing out her annual assessment letter last year. This is annual assessment is the thing that gets everybody's attention because there's a letter that's produced, and that letter is shared broadly around the country. But in fact, the letter is really just a derivative product of a day-in, day-out set of assessment, analysis, experimental data sampling, data gathering set of activities that involve hundreds of staff at our laboratory that day in, day out are taking care and being stewards of today's stockpile. I mentioned a moment ago that to carry out this very important mission requires a rather substantive capability base. This is not a capability base that's been developed in the last day or the last year or the last decade. This is something that is decades in the making, and it has evolved with time. You see an example here of how we talk about our research base. They're divided into 7 research foundations. Some of these research foundations, like engineering sciences and materials, date back to the creation of our first research organization in 1957. Others have come along later in time. Our research foundation in computing and information sciences was spun out of our engineering sciences research foundation in the early to mid 1990s when the NNSA began to invest so heavily in advancing high performance computing and related capabilities. We created a separate research foundation because our work in that area grew, and we began to grow our capability base. The Geosciences Research Foundation is one of our smallest. That has existed since the creation of our first research organization, but we only recently declared it to be a research foundation and manage it formally as such. And then Biosciences is also a relatively new research foundation. We're not a life sciences laboratory, and we never will be, but we found our work in the last decade, particularly in biodefense and in bioenergy, growing to the point that we needed some life sciences capability in the laboratory to provide support for that mission work. This was work that grew out of other capabilities that we have. For roughly a decade, we worked very hard to create relationships with academia and the private sector that would provide us with the life sciences capability we needed to carry out those missions that the government was asking us to do, but found that wasn't enough, that we needed to have some limited life sciences capability inside the laboratory in order to better connect and interact with academia and the private sector in those mission areas. Let's see, I'll close just by talking a little bit about the other missions that we carry out for the government. There's a very intimate relationship between those missions and our core mission. This view graph shows just a few examples. Obviously, I don't have time to go into all of these examples. I'll just call out 2. Just to illustrate the interdependence that exists between the missions we have for other parts of the government and our core mission. It is to the point today to where for some of those missions, obviously we couldn't do those missions were it not for our core mission, but the reverse is also equally true, that there are aspects of those other missions that make it possible for us to carry out our core mission, and without them we would not be able to carry out our core mission. A good example of that synergy is the top one that you see here, and it's in the area of radars. Up until the radar for the W76-1 Life Extension Program in the last decade, our laboratory had, from a nuclear weapon perspective, had no R&D in radars in almost 20 years. And we were able to sustain the capability in radar design and development and all the underlying capability base and be ready to support that life extension program in the last decade because we have a program in synthetic aperture radars that grew out of our LDRD program. It grew out of the very capability base that made it possible for us to carry out our core mission for the decades before that. And because we had that program, we're able to sustain that capability, stay on the cutting edge of R&D and technology, and maintain a high state of readiness from an R&D perspective to support our core mission. And then at the bottom of the view graph is another excellent example, but touching another part of the work that we do for other government agencies. And the capability here that's at the core of this is our expertise in the compatibility of hydrogen with metals. It's a very important capability for the design and development of gas transfer systems, which are a key component in nuclear weapons and one of our responsibilities. But because we have developed this expertise over the decades, we're able to support the country, and in this case also the state of California, in helping establish the technical basis that will be necessary to qualify hydrogen refueling stations. Turns out that this is a very difficult problem because you're going to have hydrogen right up against metals, and in order to have these refueling stations in our neighborhoods and in our cities and communities, there has to be a solid technical basis that regulators and the state authorities who license these fueling stations can have confidence that when they are created that they will be done so safely. So it's just another example of how we use the capabilities from our core mission to help in other mission areas. And I think with that, in the interest of time, I will end, and back to Roger.
Wow. When I was in charge, no one stayed on schedule. These guys did great. I'd like to make just a couple closing remarks, and then we'll open the floor for questions. I'm looking for, I think we probably can go until 10, yeah? So, deterrence, I've been on a couple of National Academy studies looking at terrorism and deterrence, and we could never get a really good definition of deterrence. It's a very difficult thing. But the most important thing to remember is you cannot have deterrence if you don't have confidence yourself. You can't expect your enemy to be deterred in the absence of your own confidence. Now, Admiral Haney did a wonderful job talking about STRATCOM, and have such great admiration for the military. They have confidence in their stockpile. It's getting smaller and smaller. But the enemy is deterred by the confidence that, first of all, our systems will work. They have to assume that. But second of all, the resolve of the military and their willingness to engage in whatever it takes to deter aggressive action against us. I want to turn for a moment, though, to what the subject of this panel was. I'm a nuclear physicist and experimentalist, so I understand very well the history of that. We discovered the neutron in 1932. That wasn't very long ago when you think about the Manhattan Project. And yet, in the Manhattan Project, we brought the best and brightest of science right on the cutting edge, which is where nuclear was at the time. The Niels Bohr, the Fermis, the Oppenheimers, the Tellers, even the Einsteins together to do something that had never been done before, to challenge the edges of science, but to bring us to the edges of something which was enormously destructive, had the potential to be something that could destroy the world. We came to the edge of a capability which, if we had made a mistake, could have been catastrophic for the world. But at the same time, in fact, it slowed tremendously during the Cold War, smaller conflicts. And so while we were at great risk, at the same time, the deterrence acted to bring broader deterrence than just nuclear war. We knew at the time we went into the 1980s when budgets were falling that more and more the deterrent capability from the science and the lab's point of view would rest on our capabilities as labs. A critical element of deterrence is not only the belief of the military that we have done our job competently and that the systems are reliable, safe, and secure, but in the enemy's mind that no matter what the technology might bring, that we're in a place where we can respond rapidly to provide the military with whatever is required to satisfy the deterrent policy of the United States. This is no small thing to do, especially in this unprecedented world of trying to live without the ability to fully test something which you can never, through computing and science, really get at exactly, as our speakers pointed out. I want to close this and open for questions by simply reminding you that this is a unique establishment. These people on the stage represent a civilian capability of the cutting edge of science and technology and engineering in the United States. And what's more interesting than all is they have a total monopoly of the knowledge required, not only to design and build weapons, but to maintain them and make them reliable. There are no government employees, no military people that do that job. It is a unique establishment that was set up in the Manhattan Project and has been pursued until this day. And while industry is closing its research and development laboratories and less money is spent on it, today we spend a large amount of money, often resented, but at the same time we spend a large amount of money to ensure that the young people that come to these laboratories will be able to follow on to the traditions that were started with Oppenheimers and Fermis and Bohrs, to assure that the very best, the cutting edge of what is American, U.S., Western science and technology is applied to something which could be desperately destructive, but at the same time acts through deterrence to try and minimize the destructive capabilities that might threaten our country.